Let me tell you something that's been bothering me for a long time. Back in 1981, I stood up at a conference at MIT and said something that, frankly, most people in the room thought was crazy. I told them that nature isn't classical, damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical. Otherwise, you're going to have one hell of a time computing anything meaningful. Now, I'm not the kind of guy who goes around making predictions. That's for fortune tellers and economists, and I'm not sure which one is more reliable. But I could see something back then that was so obvious to me, so fundamentally clear, that I couldn't understand why everyone else wasn't screaming about it. Classical computers, the ones we were building, the ones everyone was so excited about, they had a fundamental limitation. They couldn't think like nature thinks. And that limitation, I knew, was going to become a very big problem. You see, I'd been working with quantum mechanics for most of my career. I'd spent years at Los Alamos during the war, calculating and computing, and later I developed Feynman diagrams, which were really just a way of keeping track of what the hell was going on in particle physics. And through all that work, through all those calculations, I kept bumping into the same wall. When you try to simulate quantum systems on a regular computer, the amount of information you need to track grows exponentially. Not just a lot, exponentially. And exponential growth is a monster that will eat any computer you throw at it. Here's what I mean. Take a simple quantum system, say 50 particles interacting with each other. Nothing fancy, just 50 little quantum objects doing what quantum objects do. To describe that system completely on a classical computer, you need to track something like 2 to the power of 50 different states. That's about 1,000,000 billion possibilities for 50 particles. Now try 100 particles, or 1,000. You see where this is going? It's not that we need bigger computers, it's that the whole approach is fundamentally wrong. So I started thinking, and this is the part that got me excited, what if, instead of trying to simulate quantum mechanics on a classical machine, we built a computer that actually uses quantum mechanics? What if the computer itself was quantum? Then you wouldn't be fighting against nature, you'd be working with it. The idea was simple, really. In a regular computer, you have bits, zeros and ones, on or off, very clean, very classical. But in a quantum computer, you'd have something I started calling quantum bits, though other people later shortened that to qubits. And here's the beautiful thing about qubits. They don't have to be 0 or 1. They can be both at the same time in what we call superposition. It's not that you don't know which one it is. It's that it genuinely is both until you look at it. Now, I know that sounds like mystical nonsense. People hear about quantum mechanics and they think it's all about consciousness and observers and cats in boxes. But it's not mysterious at all when you actually understand the math. It's just how nature works at small scales. The particle doesn't have a definite state until it interacts with something else. That's not philosophy, that's physics. And once you accept that, you can start thinking about how to use it. The trick is this. If you have 50 qubits, they can exist in a superposition of all 2 to the 50 states simultaneously, not one after another, like a classical computer checking each possibility. All at once, and when you perform operations on those qubits, you're performing operations on all those states in parallel. It's like having 1,000,000 billion computers working on your problem at the same time, except you only built one machine. Of course, it's not quite that simple. There's a catch. When you measure the qubits to get your answer, the superposition collapses. You only get one result. So you can't just run any calculation and expect to get all the answers. You have to be clever about it. You have to design your calculations so that the wrong answers interfere with each other and cancel out, while the right answer gets amplified. It's like tuning a piano, except the piano is made of probability waves. I worked out some of the basic principles back in the 80s. I described how you could simulate one quantum system with another, how you could use controlled interactions to perform logical operations. The conference where I presented this was full of very smart people, and most of them were polite about it, but I could tell they thought it was interesting theory with no practical application. How were you going to build such a thing? How would you keep the qubits stable? How would you prevent errors from destroying your calculation? Those were good questions. I didn't have all the answers, but I knew that eventually someone would figure it out, because nature had already figured it out. Every atom, every molecule, every single electron is already doing quantum computing all the time. We just had to learn how to harness it. Let me tell you about 3 things I predicted that actually came true. Not because I'm some kind of genius prophet, but because when you understand the fundamentals, the consequences become clear. The first prediction was about simulation. I said that quantum computers would be the only way to truly simulate quantum systems. Molecules, materials, chemical reactions, things that classical computers would choke on. And you know what happened? About 10 years ago, researchers started using early quantum computers to simulate simple molecules. Hydrogen molecules, lithium hydride, small stuff. Not impressive by chemistry standards, but spectacular by computing standards. They were doing calculations that would take classical supercomputers days to approximate, and the quantum machines were getting the answers in seconds. Now companies are racing to simulate larger molecules, drug compounds, catalysts for industrial processes, materials that could revolutionize energy storage. The pharmaceutical industry alone spends billions of dollars on drug development, and most of that is trial and error because we can't accurately predict how molecules will behave. Quantum computers change that equation entirely. I said back in 1981 that simulating nature requires a quantum simulator, and that's exactly what's happening now. The second prediction was about cryptography, though I didn't think of it that way at the time. I was focused on physics, on simulation, on understanding nature. But other people, smarter people in some ways, realized that quantum computers could break the codes that protected all our digital communication. You see, most modern encryption relies on the fact that certain mathematical problems are very hard for classical computers to solve. Factoring large numbers into primes, for instance. A classical computer trying to factor a number with hundreds of digits would take longer than the age of the universe. That's what keeps your bank account safe. But in 1994, a mathematician named Peter Shor figured out that a quantum computer could factor those numbers efficiently, not in the age of the universe, in hours, maybe minutes. Everything we thought was secure, all the encryption protecting banks and governments and military secrets, it would all become vulnerable the moment someone built a large enough quantum computer. I didn't predict that specific algorithm, but I knew that quantum computers would be able to do things that classical computers couldn't even approach. And here was a perfect example. Today, the race is on. Governments are pouring billions into quantum computing, partly for the scientific benefits, but also because whoever gets there first will be able to crack everyone else's codes. At the same time, other researchers are developing new encryption methods that even quantum computers can't break. It's an arms race, and it started because of a theoretical idea I talked about at a conference 40 years ago. The third prediction was about the nature of computation itself. I argued that the universe is fundamentally quantum, so the ultimate limits of computation must be quantum as well. Classical computing, no matter how advanced, would always be a subset of what's possible. There would always be problems that quantum computers could solve that classical computers simply couldn't, and this prediction has been proven in the most dramatic way possible. In 2019, Google announced that their quantum computer had achieved what they called quantum supremacy. They ran a calculation that would take the most powerful classical supercomputer 10,000 years to complete, and their quantum machine did it in 200 seconds. 200 seconds versus 10,000 years. That's not an incremental improvement. That's a completely different category of capability. Now, some people argued about whether the specific calculation was useful. It was a contrived problem designed to showcase quantum advantage. But that's not the point. The point is that quantum computers can do things that classical computers cannot. Period. The gap exists, and it's enormous. What matters now is figuring out how to use that gap for problems we actually care about. So why do I say quantum computing will collapse everything we know? That word collapse is appropriate in more ways than one. In quantum mechanics, we talk about wave function collapse, the moment when possibilities become actualities. And that's exactly what's about to happen to our world. Think about what's coming. First, the entire infrastructure of digital security is going to need to be rebuilt. Every banking system, every government database, every military communication network relies on encryption that quantum computers will eventually crack. we're not talking about minor adjustments. We're talking about replacing the mathematical foundations of digital trust. That's a collapse of the current order. Second, drug discovery is going to be transformed. Right now, it takes an average of 10 years and billions of dollars to develop a new drug because we're basically guessing and testing. With quantum simulation, we'll be able to model exactly how molecules interact with biological systems. We'll design drugs computationally before ever synthesizing them. The entire pharmaceutical industry will have to restructure itself around this new capability. Third, materials science will undergo a revolution. We'll be able to design materials with specific properties from first principles, superconductors that work at room temperature, batteries that store 10 times more energy, solar cells that approach theoretical maximum efficiency. These aren't fantasies. They're straightforward applications of accurate quantum simulation, and they'll displace entire industries built around current technologies. Fourth, artificial intelligence will reach new capabilities. Many AI problems are fundamentally optimization problems, and quantum computers excel at optimization. We'll be able to train models that are currently impossible, solve logistics problems that currently require approximations, and find patterns in data that are invisible to classical analysis. And fifth, and this is the part that excites me most, we'll finally be able to ask deep questions about reality itself. What happens at the boundary between quantum and classical? Can we simulate the early universe? Can we understand consciousness as a quantum phenomenon? These aren't just philosophical questions anymore. They're computational questions, and we're building the tools to answer them. Now, I want to be honest with you, because that's something I care about deeply. I'm not saying all of this will happen tomorrow. Building practical quantum computers is extraordinarily difficult. Qubits are fragile. They decohere, which means they lose their quantum properties when they interact with their environment. We need to keep them isolated and cold, colder than outer space. We need to develop error correction schemes that can handle the noise. These are hard engineering problems. But here's what I know. The fundamental physics works. We've proven that. The algorithms exist. We've discovered many of them. And the engineering is progressing faster than most people expected. 20 years ago, people thought practical quantum computers were 50 years away. Now companies are offering quantum computing services over the cloud. We're not at the finish line, but we can see it from here. What I want you to understand, what I really want you to take away from all of this, is that the universe is stranger and more wonderful than our everyday intuitions suggest. When I first learned quantum mechanics as a young student, I was shocked. This couldn't be how nature works, I thought. It violated everything I thought I knew about reality. But nature doesn't care what I think. Nature does what it does. And our job, as scientists, as thinking beings, is to figure out what that is and how to work with it. Quantum computing is the ultimate expression of that philosophy. Instead of fighting against the weirdness of quantum mechanics, we're embracing it. We're saying, okay, nature works this way, so let's build machines that work this way too. And when we do that, capabilities that seemed impossible become possible. Problems that seemed unsolvable become solvable. The boundaries of what we can know and do expand in ways we're only beginning to imagine. I spent my whole career trying to understand how the world works. Not because I wanted to build things or make money or become famous, though some of that happened along the way. I did it because I wanted to know. The pleasure of finding things out, that's what drove me. And quantum computing represents the greatest tool for finding things out that we've ever created. So when people ask me what I predicted, I tell them I didn't really predict anything. I just paid attention to what nature was telling us. The quantum world is real. It's not a mathematical abstraction or a philosophical puzzle. It's how atoms and molecules and light actually behave. And once you take that seriously, once you really internalize it, then quantum computing becomes not just possible but inevitable. The collapse is coming, not in the catastrophic sense, but in the transformative sense. The way we compute, the way we encrypt, the way we discover, the way we understand, it's all going to change. And the foundations for that change were laid down in a conference room in 1981 when I stood up and said something that everyone thought was crazy. It wasn't crazy, it was just ahead of its time. And now, finally, the time has caught up. If that doesn't excite you, if that doesn't make you want to learn more, to think harder, to question everything you thought you knew, then I don't know what will, because this is the game, this is the adventure, and it's just getting started.